The first model we're going to look at of the atom is the Bohr model. And we're going to start out by looking at this neon light. So the orange there, the orange lights here, that's an actual neon light. Those are tubes of glass that have neon gas in them. And it's not orange because the glass is orange. It's orange because when you run electric current through neon gas, it glows orange. And this blue part here is going to be a different kind of gas. These neon atoms inside the tubes absorb the electrical energy and then give it back off as light. These don't say anything like that one did. That one was advertising something. This is a mercury lamp. This is a glass tube, and it's got mercury gas inside of it. We pass electricity through it, and it glows blue. Over here, this is a hydrogen lamp. Glass tube with hydrogen gas in it, pass electricity through it, and it glows pink. The fluorescent lights in the ceiling are doing the same thing. Fluorescent light does not have a filament in it like an incandescent light bulb does. You've got these two metal caps at the end, you've got a glass tube, and it's full of gas, a mixture of gases. And depending on what gases are in it, you can get a cooler light or a warmer light. But you turn the electricity onto it, and the gas starts to glow. If we take the light from, say, that hydrogen lamp, and do the same thing that we did with the incandescent light bulb earlier, pass it through a slit and then through a prism, instead of giving us a spectrum, a continuous rainbow, we get lines. We get 4 different lines, and in between is nothing. And this is the interaction of matter and light that sparked a lot of the developments in understanding of what's going on inside of the atom. Because they observed this and they're like, what on earth? Here's light coming out. You would expect it to make a rainbow. Maybe not the whole rainbow because there's, it's got a particular color to it. But they did not expect these very sharp, distinct lines like this. So the light emitted by hydrogen has distinct wavelengths that are specific to hydrogen. You could make all kinds of different hydrogen lamps, and they're all going to give you those same lines, exactly the same colors. You can measure the wavelengths, they'll have the same wavelengths. So here are 4 different spectra. This is white light from the sun or from an incandescent light bulb, and you get this continuous rainbow. You don't have any gaps in it. There's light of different colors all the way across. The hydrogen light will give you 4 lines. If you do that with helium, you get more lines. If you do it with neon, you get more lines. Neon has a lot more lines, and yet it is still not continuous. There are specific lines. It's giving off light of particular frequencies. These are called emission spectra because it's the light that something emits. And so any individual element will give an emission spectrum that has distinct lines in it. So why does it do that? Well, Niels Bohr developed a simple model to explain this. The question they were interested in is, why do excited atoms only emit light at particular wavelengths? So this is what his model looks like, and it kind of resembles the solar system. Here you have the nucleus, that's where all the protons and neutrons are, in the center of the atom, and then around them, going in orbits, are the electrons. So the electrons are like the planets, and in the center is like the sun. That's the nucleus of the atom. And so students like this model because it's simple and it's easy to understand. And so here's another orbit, so you can have electrons in there, and they're going around. Okay, so we've got orbits. The orbits are numbered, 1, 2, 3, 4, 5. And the distance from the nucleus for those orbits is fixed. So the n equals 1 orbit is always a particular distance from the nucleus, and the n equals 2 is a particular distance. We say those are quantized. It's a little bit like rungs of a ladder. They're specified by quantum number n, so 1, 2, 3, 4. Over here we have a picture of a ladder. It's kind of a weird ladder because the rungs aren't evenly spaced. But this would be like the n equals 1 orbit, the n equals 2, n equals 3, n equals 4, 5, and 6. So they're varying in their distance from the nucleus. But this one is always the same distance, and that one's always the same distance. And you cannot be in between. Can you stand right here between the two rungs of the ladder? No, you can't. There's nothing to stand on. You can be on the second rung or the first rung. You cannot be in between. And this is a concept. This is the concept of something being quantized. Our monetary system is quantized. There are pennies and nickels and dimes and quarters and 50-cent pieces and $1 and $2 and $5. There's no $3.52 coin or bill. There are only certain denominations, and you can't be in between. Grades in school, you're in first grade or you're in second grade. You're not in between, one or the other. Stairs are quantized. You can stand on the first step, you can stand on the second step. You can't stand in between. You can pass between the two, yes. But it's impossible for an electron to exist between the orbits. Your book doesn't really go into this, but like Wyndham alluded to, when you are going up a ladder, for a brief period of time, you are between the rungs as you're moving from one to the other. The electron doesn't even go between. It's in one, or it's suddenly, instantly in the next. We call that a quantum leap. I don't know if you remember that TV show, Quantum Leap. He would just go somewhere else without going there. He would just be there. That's a quantum leap. And that's because of the wave particle nature of the electrons. Yes, we'll talk about that in a minute, about them giving off light. So these different orbits have different distances from the nucleus, and they have different energy levels. If we think of this ladder in terms of potential energy, as we go up the ladder, we're gaining potential energy. As we're getting farther above the ground, your potential energy is greater. So what happens is, here's our hydrogen atom with its nucleus and its one electron. When energy comes into the atom, the electron can absorb that and become excited and go to a higher energy orbit. It doesn't go through those, but it goes here and then, it went to that one. It's like that. It's one place, it's the other. It's never in between. But it can move up to a higher energy level. We call that an excited state. It's not stable. So it'll be up there, and then it's going to eventually relax. It could relax down all the way to where it started from, or it could relax down one level at a time. But when it relaxes down, that energy that came in has to come back out. And that's where the light comes in. So when that excited atom relaxes back down, the energy that the electrons absorbed are given off, and the energies that they have correspond to visible light. And so we see light coming out of the atoms. And what they're releasing, each electron moving from one level to the next is releasing one photon, one piece of energy. That piece of energy has a wave property, so it has a wavelength and it has an energy. And it's also called a quantum of light. The light emitted by excited atoms is going to have specific lines at specific wavelengths because it corresponds to specific transitions between orbits. So for hydrogen, here are 3 of the lines that we see in the hydrogen spectrum. And the red one corresponds to a transition from n equals 3 to n equals 2. And the blue-green one corresponds to n equals 4 going to n equals 2. And the violet one corresponds to n equals 5 down to n equals 2. This wavelength corresponds to an energy. The energy of that photon is equal to the difference in energy between these 2 orbits. The difference between these 2 orbits is a smaller amount of energy, a longer wavelength. These 2 orbits have, the difference is lower energy, and so the wavelength is longer. So from looking at the lines, they were able to calculate the energies of the electrons in these different orbits. And it was really cool, and the math all worked out great for the hydrogen atom. The hydrogen atom is the simplest atom. It has 1 proton and 1 electron. It's very, very simple. And this worked out great for that, and it was awesome. It predicted the lines of the hydrogen emission spectrum. It explained it. It was beautiful. And then they tried to apply it to helium, and it didn't work. It only works for hydrogen. So it's kind of marginally useful then, right? Because we don't do a lot of stuff with hydrogen. We want to know about everything else too. So it's very useful in that it's fairly easy for us to understand. We can imagine something moving from one orbit to another orbit. We can visualize that in our brains. Okay, and so it helps to give us a basis to understand what we now understand to be most likely the true model, which is the quantum mechanical model. So the Bohr model has been replaced with a more sophisticated model. It's called quantum mechanics.